This is part 2 of 3.2.3, and we're doing fiber optics. So, fiber optics are essentially a type of cable made of glass that are used to transmit data using light pulses rather than electricity. So the fiber optic cables, you need to know their structure first of all. So we'll sketch a fiber optic cable. The fiber optic cable on the inside has a core, and surrounding the core is what's called the cladding. Now, if we remember to last lesson, for total internal reflection to occur, what was the condition? So the angle of incidence has to be greater than the critical angle. What else? What about the refractive indices?
The refractive index of what it's entering has to be higher.
Okay, so the refractive index of what it's trying to enter has to be higher, greater than. No, that's not right. The refractive index of what it was in has to be greater than the refractive index of what it's trying to enter. So, the core has a large refractive index, large N, which means that light moves slower through the core. And the cladding has a small n, which means that light travels faster through it. So here we've got that n core is greater than n cladding. Put a subheading called the cladding. So number one, the cladding increases the critical angle so that you lose non-axial rays. So anything that's not traveling down the fiber optic, you want to get rid of those rays. You don't want the rays bouncing around too much. So it increases the critical angle to lose non-axial rays. Then the second thing it does is that it protects the core and adds strength to the cable. The core itself is usually made of very, very thin glass or some other transparent material, but it's very thin and fragile. So 2, it protects and adds strength to the core. So, if we do a horizontal sketch, So the cores are made very, very thin. So two things can happen here. Either that light goes straight through the core and carries on the horizontal line, which is what you prefer, or light hits the boundary between the core and the cladding, it undergoes total internal reflection, and it takes a different path to reach the end of the cable. So we'll do two of those. We'll start sketching these. So in black here, we've got light that goes straight through. We can do another sketch. So now, if we had light entering the fiber optic at some angle, then rather than heading straight through the fiber optic cable, at some point it's going to strike the core cladding boundary. So we'll sketch that. So it comes in at some angle and strikes the core cladding boundary and undergoes total internal reflection. And we'll just draw our normals at those points. So you've got a normal there, you've got a normal there, and you've got a normal there. Now your fiber optic signals, they're not sent as a continuous stream of light, rather it's sent as pulses. So the light is flashing very quickly. Now if some of your light goes straight through and some of your light goes in at angles, then the light that went in at an angle, if they came from the same pulse, then the light that's reaching the receiver that has been undergoing total internal reflection will reach there at a later time than the light that just went straight through. So the pulse that came out versus the pulse that was received on the other end did not have the same width, because some of the light took longer to travel through that core by doing total internal reflection and getting there at a later time. And that's called pulse broadening. Now, if you have data traveling through a fiber optic cable, the faster you can pulse your light, the more data you can send. But due to total internal reflection, and you get pulse broadening that's being received, you then have to slow down your pulses on the other end so that you don't have data streams interfering with each other. Because if you send one pulse, you send another pulse right after it, and some of the light from the first pulse still hasn't reached the receiver, and light that went straight through the axis from the second pulse went to the receiver, then you're going to have interference in your data. And your data is not going to be received correctly. So the emitter will adjust itself so that it can reach the best possible speeds without interfering with the other pulses that went ahead. So if you have pulse broadening, you slow down your pulses. So here we'll just sketch the angles. So on this one, light reaches the receiver. At a later time. due to total internal reflection. And this causes pulse broadening. So what that means is that if your input pulse looked like this, then your output was more like this. I should actually reduce the signal there a little bit. So it was broadened. Another thing that can happen is that we want some of the light to stop reflecting and to escape, because otherwise that would cause a degradation in our signal, so we'd have to slow down our signals. So if light came in this way, at a very small angle and struck, we don't want it to bounce up and down, because that will mean that the signal will reach at a very later time. And a very later time means that our pulse will be broadened massively. So what we want from this ray of light is we actually want it to be lost into the cladding. So this is lost in cladding. So we can say here that if the angle is too small, then the ray is lost to the cladding. And this prevents excess pulse broadening. Finally, we'll talk about types of dispersion. So the first one we'll start with is modal dispersion. So for this, I'm going to make our fibre optic cable again. So if we had our little pulse here, so that's the signal of our pulse. It's an on and off, so it's a flash of a light. Now from that flash, we get some light going straight through, like so. We get some light going at some angle. And here, if you measure these lengths that are being drawn, you'll see that they've got different lengths. The first line I've drawn and the path taken by the second one. And then I'll draw a third one as well. So that gives us an output which looks more like this. So you had one flash of light, but from one flash of light there are rays that move in different angles. So they enter the core at different angles, which means that they strike the cladding at different angles. So the path that they take is different. And if they take different paths, that means there's a different amount of time that it takes for each of those rays to reach the end, causing a broadening of the pulse. Yeah. Which dots? The dots I've done all on the outside, that's just a consequence of me trying to draw multiple arrows. So these dots don't exist. And I can't even delete them properly. Right, these dots, they don't exist. It's just that when I use the arrow tools or the line tools, if I try to draw another line from where the first line finished, I have to click out of that line before the software will let me do that. So that's just me clicking out of it and ended up putting little dots on the outside. So these dots here, they don't exist. That's just because of software. If I drew it freehand, I wouldn't need to do that. Okay, next. Notice I did this with monochromatic light. Now I'm going to do it with non-monochromatic light. So the next one is called material dispersion. To do it with non-monochromatic light though, I would have so many rays of light that it'll be too much to do. So what I'm going to do is I'm going to emit all of the different rays except for one that travels at some angle and strikes the cladding. So that way we can actually see material dispersion better. So we draw a fibre optic again. Now, this time I'm going to have white light coming in, and I'm going to draw it, because I can't draw a white arrow, I'm going to draw it as a black line first. And what I'll do is I'll just put a dotted line for the axis. That will make it easier for me. Okay, so we'll do our first arrow entering at some angle. And when it enters some angle, the light begins to disperse. Because if that is white light, and let me label that as white light because I did a black line. So this is white light. So the light disperses because different wavelengths and frequencies of light refract at different amounts. So you'll get red striking like that. And then I'll do a green. So green will refract more than red. And then we'll also do blue. So that gives us the three colors. So now you can see if you use white light in a fiber optic, you don't just get pulse broadening due to modal dispersion, that different light rays enter at different angles, but also you get another type of dispersion, which is that white light is made of different colors. And those different colors with their different frequencies, they refract at different amounts. So each of those white rays that enter, there are white rays entering at different angles, but also each one that enters then splits into their component colors, which then all go off into different angles. So you get even more pulse broadening had you used white light. So typically when you see a fiber optic cable, they'll use monochromatic light, usually red light. If you've got a TV that's semi-modern, or you've got an amplifier at home, if you look at the back, you'll see a jack that says SP-diff. And SP-diff use fiber optic cables to transmit audio. It's usually got a cover on it. If you were to poke the cover open, you'll see that there's like a little red light in there. So those are used to transmit audio to amplifiers. Now, at the other end of a fiber optic cable, so the receiver end, because there's a change in the pulse, and sometimes the pulse is also corrupted a little bit, there are parts of it that are missing. So we've drawn the pulses as having sort of a constant amplitude. But what you get on the end might not necessarily have a constant amplitude, it might even have breaks within the pulse. So on the other end, you need a digital circuit that will then interpret that signal and fix any errors. So typically, we'd use digital signals for fiber optics rather than analog ones. The reason why you won't use an analog, again, if we had a sinusoidal wave, if it was a continuous sinusoidal wave, then with pulse broadening, we would not be able to make out the distinctions of a sine wave. So we have to use discrete pulses. And that's the end of 3.2.3.